Thank you for being with us today. We are Team 6, Panther Cargo, myself Arjo, this is Andres, there's Nestor. Our academic advisor for this project was Dr. George Dulikovic. Our main objective for the team was to enter the SAE Aerodesign competition held in Brazil at the end of October. Due to the fact that the team wasn't able to register for the competition, the team decided to still press on with the project as if they were going, and modified the objective to designing, building, and flying a radio-controlled airplane still capable of flying in the competition. Part of our motivation was that the team not only wanted to build an airplane that was capable of competing in the competition, but an airplane that could win the competition. To represent FIU at an international level in Brazil, to leave a legacy behind for future students to follow, which led to the idea of creating an aerospace engineering club at FIU, which would also help promote interest in aerospace engineering.
Some of the global learning components of our project that we tried to tackle were global awareness, and global perspective, and the global engagement. In terms of the global awareness, we are convinced that our research and our findings and our achievements will impact future projects as much as previous projects that participated in this competition impacted our own research as they did. There's an ethical awareness part of this project, which is the rules. You have to follow the rules, you have to obey the rules, you can't deviate. There's sanctions if you cross multiple lines, design restrictions. So we want to keep our project within the limitations. In terms of the environmental impact, we try to use as much as possible recyclable or reusable materials, metals like aluminum, steel, a lot of wood, and we avoided using any lead, for example, which was prohibited by the SAE committee because of its poisonous nature, and of course as well as carbon fiber, since it does not biodegrade. Some other standards, just to list some of them, the ones that we used. Of course, the SAE Aerodesign rules, we have to abide by them, follow each and every single one of the regulations. The FAA is a big one. They have a document that states and regulates the usage of this type of aircrafts for recreational purposes. We cannot do it for financial purposes. We can fly it only up to 400 feet high and nowhere close to airports. There's a lot of regulations that we have to obey in terms of the FAA to stay within the law. AMA is the Academy of Polar Aeronautics, so they're the ones that issue the insurance and the permit to fly these types of aircraft. Not anyone can fly, you need to have a special permit, and we had to fly a pilot that had all the documentation in place. In terms of the competition itself, it's divided in mainly three categories: the micro, the regular, and the advanced. Due to the team's limitations in terms of money, in terms of knowledge, and in terms of applicability as well, we decided to go by the regular class. The main problem statement of this competition is be able to lift as much weight as possible of an aircraft that weighs less than 44 pounds or 20 kilograms. It has to have a cargo bay, which is where you put the cargo, the payload right there. That has no less than 4,800 cubic centimeters, and 6 orthogonal phases. This is by design by SAE rules. It needs to have that. A major geometric design restriction is that the top view from the airplane, the area as it's seen from the top view, platform view, cannot exceed 0.775 meters squared. Everything counts: wing, elevator, fuselage, motor, everything counts against you. This is taken from the SAE design rules. We have to be able to take off within a time span of 3 minutes from the moment the indication is given. We have to take off within 200 feet runoff, and be able to land within 400 feet as well. Some of the limitations. The rules give us, for engines that we can choose, we can only go with gas-powered engines. They gave us these engines. and we had to compare them and kind of do trade studies to see which one of them was the one that suited the most this particular aircraft, and we could not use metal propellers by rules. In terms of our particular design, we started choosing the airfoil. The airfoil, it's a very important part of the aircraft, as we all know. Its profile is the one that dictates how much lift you will get, and we wanted as much lift as possible. So we wanted an airfoil with a lot of fairly amount of camber. Now we had these 5 concepts that came out of the literature that we researched. We compare them all, of course, in terms of strength and manufacturability, performance, lift to drag ratio. The problem with the ones that gave the most amount of lift is the fact that they were very thin in the trailing edge. That's their characteristic usually. So in terms of taking this to real life, to manufacturing this type of airfoils, it's very risky and difficult, because if you have any accident, it'll break very easily. So we finally chose, after comparing them all, we chose the Upler 423, which has a fairly thick trailing edge, but it still provides very good amount of lift to drag. We came up with several concepts before achieving our final design decision. This was the first one. Its main characteristic is that the payload carrier, the metal component you see right there, was right underneath the wings. This, we wanted to do it because we wanted to reduce as much as possible the area that this component was projecting from top view, so that we could use this area somewhere else, longer wings, thicker wings, somewhere else. So we wanted to kind of hide this component underneath the wing. And the drawback is that this frontal extra area would obstruct the air coming from the propeller, and potentially cause a reduce in lift. Of course, it was a conventional design. In terms of the tricycle landing gear, it was very conventional. The tail was a conventional tail. So we'll talk about the next design concept.
Yes, as Andres was saying, after Concept A, we went to Concept B because Concept A was just shown to have too much frontal area right behind the propeller, which was not a good characteristic. So in Concept B, what we decided to do was to remove that extra frontal area caused by in Concept A and have the cargo bay distributed throughout the entire wingspan. Once we did that, as appropriate, we did some structural analysis. In this case, we simulated a 5G in-flight analysis as well as a hard landing analysis. And the problem that showed up during Concept B was that during our structural analysis, it was deemed that the wings were going to have too much displacement. So rather than continuing any further, that project, that prototype, or that concept was rejected. This led to Concept C. In Concept C, we took the payload and we located it longitudinally in the fuselage, and we also took we tried to minimize the platform area by having a thin boom. Unfortunately, once we started looking at the various mounting options to mount that boom to the fuselage, it just proved to be a little bit too complicated, and we also had some concerns that it was going to be too weak. That led to our final prototype. In this design, we went from the boom to just a conventional empennage support, which proved to it eliminated our concerns as far as our mounting concerns, and that's what our final prototype looks like. Okay, and then it was time, once we had our prototype concept, it was time to start doing some more specific dimensions for the whole airplane. And at this point, there were some decisions we had to make. There were some numbers that we had to choose, such as the aspect ratios, taper ratios, tail volume coefficients. And there were some numbers that we had to arrive at, such as the center, the coefficient of drag, or the lift to drag estimations. Those were calculated and were estimated. Once we had the aircraft completely sized, it was time to start building it. So what we did was we found ourselves someone who did laser cutting of wood products, and this person was able to cut all our parts on a laser cutter. And then here we see the right wing as we were putting it together. Now, one of the things that we deem very critical during our project is to maintain a center of gravity precisely, or as much as possible, where we wanted it. So as the aircraft got built and as components were being added, every so often we would take, let's go ahead and do another validation check of our CG before going any further, in case we still needed to make some adjustments. Because one thing we didn't want to have to do was to have to add counterweight, because that would really just take from our desired payload capacity, so we never did have to do that. Our job?
Power is just as important of an aspect for this project as is lift, because without power, we can't generate lift. As Andres mentioned before, we had a list of engines that were given to us by SAE that we needed to choose from. After doing a matrix on comparing these different engines to different aspects of them as horsepower, RPM, and thrust, we decided to choose the Magnum 61 XLS, not only because of those factors, but also because of its availability and reliability in the market. Now, choosing the right propeller is the same as choosing the correct tire for a car engine, because the research suggested that the 13x4 propeller was the most optimum propeller for this engine. As you can see in the chart, the research done by University of Michigan students, they did a dynamic thrust test with various propellers, and the 13x4 was the most optimum and provided the most amount of thrust at different velocities. After knowing the fact that the 13x4 propeller was the most optimum, we decided to do some test validation of our own. As you can see in the chart here, we compared different propeller sizes, some recommended, some not. And the 13x4 was the clear winner in static thrust and measured highest in RPM. Choosing the correct landing gear was very important for this project, because when we were at the design stage, we knew this plane would potentially lifting 30 to 40 pounds. And so, knowing that there could be possible hard landings, we had to choose a landing gear that could withstand such sort of stress. So we decided to go with a steel nose landing gear, which is 3/16 in diameter in inches, and an aluminum main, a 6061 T6, 1/8 inch in thickness. The way our timeline took shape is when a lot of the dates for the competition came out, such as when the flight video was due, as well as the final report for the competition. And knowing these goals that we had to meet, we set up our timeline accordingly to make sure we met these deadlines. And I'm glad to say that we did meet the deadlines. Our actual cost for building this airplane ran us around $1,100. Main component of our cost was the materials, which not only included purchasing of materials such as balsa and plywood, but also getting the material CNC cut, profile cut, the way we needed for the wings and the fuselage.
Once we had a lot of our analysis done, and we knew the coefficients of drag, and as Arjaf explained, we knew what we expected as far as thrust. Then it was time to do some predictions of our performance. We knew that our biggest limiting factor was our takeoff distance of 200 feet. So we created a spreadsheet. We put all the formulas in there where we tried to come up with, okay, what at different loads, and then our takeoff accelerations that based on what we had, what could be our projected takeoff distances. And so here we see our final one here, which was 192 feet, which was within the 200 feet that we limited ourselves to. And then here we have our actual test results, and these were on the various dates. And as you can see, the 27th of July was our first flight, which was within the competition rules, and we made our video accordingly. And then going all the way to on the 16th of November, we did one final flight, and during that flight we were able to lift 20.1 pounds, We made some variations, some changes during the whole testing process, whether it was softer tires or tried different propellers just to make sure. And then on our final configuration, we had no brakes, and we basically flew the aircraft the way we wanted it, and it flew pretty well that last day. And then here we have, this is an actual excerpt from the competition from Brazil. This is what they published, and this is what we use to measure ourselves. So had we had the opportunity to go to this competition representing FIU, how might have we performed and compared ourselves? Now, there are other things that go into this, into their point system, such as how do you deliver a report, the report itself. Obviously, we can't measure ourselves and other teams that were there. But based on the payload carrying capacity alone, which was the only thing we can objectively measure, an argument can be made that we possibly could have placed ourselves in, at least in the top 10. Oh, and then one of the things that at the beginning of the competition, we didn't have a pilot. And since going to Brazil, we thought we might have to rent somebody over there. And that was a big risk and a big unknown. And we might have to make an airplane super conventional and super stable because we just didn't know what to get. So we started to look for our own FIU pilot within the FIU students that could hopefully help us out and fly well and so on. So we were very lucky in that sense. We were able to find Mr. Kishan Kalpo, our pilot, and at this point I would like to introduce him to you.
Thank you, Nestor. Good morning, everyone. I've been flying model airplanes for 6 to 7 years now. And an important thing that you learn in the hobby is that you try to keep as much weight out of your airplane as possible. But that was not the case with this competition. And I have to say that flying the airplane really took me by surprise, because I really didn't expect the plane to be able to lift the payloads that we put in there. But as you can see later in the video, here, the airplane takes off very smoothly while carrying 20.1 pounds. You can see that I'm rolling it early here before getting enough lift, but it takes off just fine. The wings stay level, even at a slow speed, and while still carrying a heavy payload, the airplane is still able to just stay stable and predictable, and there's no hiccups or any surprises in its flight characteristics. So all we have to do is make one circle. So I'm making the final turn here for the landing, which is right here. I'm starting to bank it, and the airplane does not lose any lift while turning, even with the heavy payload. It's very predictable. And here I'm lining it up to land it, and when landing, the difficult part is it comes in very fast, so I had to sway it back and forth to stop it because we didn't have brakes, but it performed just fine. Thank you.
Thank you.
Lastly, I'd like to say,
It's still here.
lastly, I'd like to say that part of our motivation was to leave a legacy behind, and I'm proud to say that we are the founders of the Aerospace Engineering Club at FIU. The purpose of this club is to participate in aerospace-related competitions, to grow the name of FIU around the world, to do some community service as well, and so we're very happy with the way the club's gone so far. We'd like to say a special thank you to Mr. Zuccarelli, who helped us design and manufacture our braking system, to Dr. Tremante and Dr. Redding to let us borrow their payload carrier as well as the remote control, to Dr. Monroe for his outstanding support in helping us with paying for registration costs for the next competition for the club, and Dr. Dulikrovich for being there for us the whole way throughout the semester, being our academic advisor. And we'd like to thank everyone for their support. Thank you, guys.
You know what my question's going to be. Are any of you all here in the spring?
No. The three of us aren't. He's still a sophomore.
Are you staying?
Yeah.
Can you, because I wanted to do the Engineers on Wheels with your plane.
Yeah.
It's such a great,
So he'll be here. He's the next
You're the
president
next president
for the
of the
Aerospace Engineering Club. So he'll stay in contact with us regarding the
And
plane.
Ms. Strange, the next competition airplane's already been designed. We did that throughout this semester.
Wow.
So it's already designed, the wood's already been cut, and we're going to be assembling it now.
Oh, so you're gonna have 2 airplanes?
Yeah, potentially.
Wow.
Next year,
The
yeah.
beginning of.
You're not gonna butcher this one up for the next
No,
one?
No. That's against our ethics.
Ah, that's great. It's really nice.
I guess the one question I have is, why didn't you get to go to Brazil with this? Was it too late, too early?
No. We were there the day registration opened. Unfortunately, no team from the U.S. was able to register because they made it extremely hard for us. My understanding of that is they're scared of us, and they didn't want
How
us
did
to
they make
go.
it hard for you?
So this was a
Georgia Tech
political?
didn't go, MIT didn't go, no one went. It was
We're
a-
placed in a waiting list.
Yeah,
We're
we're-
like 14 on the waiting list.
that's
Of course, only like the
disgusting.
first 5 teams of that waiting list were able to get into the competition. So we were just able to make
Too
it.
many people.
Yeah, too many people.
Oh, yeah.
Yeah.
It fills up within minutes.
Well, we could probably say if we would have gone, we would have kicked ass.
That's your role next time. to get on that
Exactly. So
list.
we're hoping
Yeah.
when the club starts participating in different competitions, we place regularly in the top 5 to increase the brand of FIU. And
Are they moving it out of Brazil? Or is it?
What's that?
Are they gonna move it out
The
of
next
Brazil?
one will be here in Florida.
Correct.
In Lakeland, Florida.
There's actually 3 competitions a year, one in SAE East, which that our next airplane is going to compete in. There's SAE West, which usually takes place like California or Texas. And then there's, those 2 occur at the same time, roughly the same time. So you can only enter one or the other.
Around March.
So we, obviously for us, East is better. And then the other time frame of the competition is in the fall frame, and then that was our time frame. So that we couldn't choose a different, say, to go to SAE East, because that's in March. So if you're on a senior design schedule like we were, the only one available to us was SAE Brazil, and that's in the fall.
Oh.
Any other questions? Quick question, because we really,
Yeah.
oh, okay, yeah, go ahead.
Yeah, I have a quick question. I'm a former SAE, FIU. I started, me and my team started the Formula program back in the day. I do know during the competitions, you usually have to do a design competition. Are you guys required to do some kind of cost analysis report or anything like that? Okay.
Well, for our senior design, we did put the cost.
Right, yeah, the same.
For the competition.
For the competition.
Not that we're aware of.
No, they have some limitations. Obviously, we didn't get to go, so it didn't affect us, but let's say a limitation on the rule would be, the teams that went there, they had to limit themselves to 15. Obviously, we didn't have that problem.
Yes, go ahead.
Just a quick comment, I guess. So first things first, I think you guys did a great job, and especially with certain things like lifelong learning and all of the other aspects associated with that. The other thing I'd like to say is thank you all for trying to perpetuate some of this stuff, right? We need to learn from previous groups a lot,
Right,
and I think that's separate from that. Okay, we all have to be critical a little bit, right? One thing I really missed, and I know you guys did this, I really missed from your presentation was the analysis that you did. I didn't see it anywhere, really, to be honest with you. I saw some numbers that were in your report, but I have no idea from this presentation how you got those numbers, okay? So be very careful with that. Know what audience you're trying to talk to here, because you're trying to impress us with your analysis at this point, not the manufacturing that you did, right? So manufacturing is an important part, but you have 20 total minutes. Those minutes are gold, right? Those minutes are gold. Don't use 8 minutes at the beginning of your talk talking about how you put the plane together, okay? Because those 8 minutes, you could have done 2 minutes of that. I know that's the hardest part, and you guys did an excellent job with project management to get it done in July, which is insane in terms of typical timelines that we see, okay? But just because you spent the most time on it doesn't mean that's what you spend the most time with on the presentation, okay? So in this part, you gotta wow us with your math and your predictions and all of those things to really to really show us that you know what you're doing in design. And I know you guys did that, and it made me a little disappointed to not see it through this part, that's all, okay?
I mean, the only thing with that is that we created a whole Excel sheet.
I
which we can
completely
go over
agree,
later.
so you gotta
But it was-
learn how to simplify.
Yeah, it was
Learn how
too
to
cluttered,
simplify.
which is why we didn't want to put it up there to confuse everyone with crazy
So
numbers,
take the
so-
steps, right, learn how to
Okay.
simplify.
Well,
That's really important.
Thank you.
To piggyback on that, could you go to your final prototype slide, please? Final prototype. Okay. You showed several configurations of the airplane, some of which have winglets.
Correct.
And we all know that winglets is an excellent tool for reducing induced drag.
Yes.
So how do you end up with a wing like this without the winglet from an aerodynamic standpoint?
I think Nestor's excited to
Yeah,
take that
we
one.
did get something like that. We did do some research on that. We researched previous teams and what were their opinions on whether or not we should use the winglets or not. But we came to the conclusion that at these speeds, in this size of an aircraft, it wasn't that much of a gain, if at all, in terms of lift and drag reduction, if we added wings, and that was an added
Wait.
manufacturing challenge.
Yeah.
So we really looked into that, but we came to the conclusion, based on the literature from previous teams, that the winglets would not add a lot of value to this project.
So to Ben's point, what would have been very nice is, even if you don't demonstrate the detailed calculations you did, provide some rationale or reasoning as to why you went from this particular example or option to this other option, or just in the final prototype, give some parenthesis to each of those items as to how you got there, kind of thing.
One thing I just wanted to do, this is 20 pounds that we carried. I want the IAB members to at least grab it to know what it feels like.
This is what the plane
20 pounds.
Yeah, this is heavy.
Keep in mind the plane is actually 13
Plus
pounds.
the weight of
Wow.
That was.
So that is 20 pounds that we
Taken up
carried.
within 200 feet though.
Oh, yeah.
When we were carrying 14 pounds, I thought, this is gonna be way too difficult. 20 pounds and it did it without problems.
So by putting
Dr.
slugs inside.
plates, that's the way we put it.
Strength.
Yeah, and also as our pilot, because at first we had to make a believer out of him. He was scared to death. So, oh, put on some more weight, put on.
No, I can bench
We
press.
think it's possible. And he was scared to death at first.
Because, like I said, after 6 years of flying,
I'm a big
you
dope
learn
man.
going out of the airport. And there's a lot of concern with adding to it, so I was very concerned with this possibly
That's
destroying
really,
the
that's
plane.
impressive.
Thank you.
It's
And
just
something
like-
I just found out with this sidebar conversation, they did all of this with the airplane clean. Normally you need flaps when you've got all these extra load and all of this kind of stuff.
Yes.
They did it clean, so that's quite an achievement.
So show us the science why you could live that.
You and your simulations.
It's
It doesn't have to be so
proprietary.
science.
Dr. Basil, I think
Yeah.
that, and this part possibly ties into Dr. Carnegie's question about the winglets. I mean, this wing is technically a forward swept wing. And when you sweep the wing forward, the outflow of the air is greatly reduced. So if you have a potential gain of, say, 3% on your winglets, you already reduced that, and now you're getting into an area where the potential benefits, you might lose them due to, say, an increase of parasitic drag, not to mention weight. So I think that part of the success that we had was, and this wing was very complicated to manufacture. I don't recommend it, and it was crazy math to get to figure out our MAC and our CG and all that, but it seemed to work very well. I think that.
It was crazy math. But
Okay, we need to move on. Thanks again.
Right.
We will